Thanks for joining. I'll talk a little bit about some of the rapid simulation tools that we've been working on here. Two in particular, FastFlood and the upcoming FastSlide web-based simulation platforms. My name is Bastian van den Bout, by the way. I work at the University of Twente, ITC, so Faculty of Geoinformation Science and Earth Observation. And I'm one of the main developers of this stuff. So I'll talk today about two tools that we're developing, maintaining, and expanding a lot. FastFlood is one of them. It's an existing tool. It's been now in a usable state for, I want to say, 1.5 years, something like that. So you can just go there and use it and find all the tutorials and material and all the stuff that I'm going to show you. Most of it is there as well. And then FastSlide, a landslide focus tool that is upcoming with a deadline for the ETU this year, because that's when I have to present it as well. So then I better have it finished. I'll talk a bit about methodology, show you a lot of demonstrations, so you know a little bit how it works and get a feel for it. And in the end, so maybe a bit of a discussion of where we want to go with these tools. So first, the flood one. I think some of you maybe have heard about this before, so I'll keep this a bit shorter. The idea is we do really rapid simulation of precipitation, infiltration, runoff, so the hydrology part, as well as the hydraulics. So predicting flood maps, flow extent, flood depths, and velocities. It's fast enough that it gives you sort of instant flood maps, right? Within a second, it's supposed to give you your results, and it allows you to also draw mitigation designs, for example, and immediately see what's going to happen here. It's free, partially open source. The algorithms are, the website is not. Runs locally, so we don't run any servers to actually do the computations. When you go to the website on your phone, it's your phone doing the actual modeling, but it's fast enough that we can do that, and it saves a lot of server costs. A lot of extra features that we've added since then: better input data sets, real-time forecasting opportunities, but we're trying to make that a little bit more robust and reliable as well. Automatic downloads of design storms, climate parameters, and automated calibration as well. All things to try to help the user with this. To summarize the methodology a little bit, this is a combination a bit of a couple algorithms and a couple assumptions that make it so fast. One of the main trade-ins that you're making here to keep in mind is that you don't get a time component anymore. We're just predicting peak flow heights, peak flood depths, peak velocities, but we're not predicting the full dynamic animation maybe of the event. We're just giving you your flood map. That's one of the things that allows it to be so fast. We combine it with a couple algorithms based on the fast sweeping algorithm. We use that in terrain correction, steady state discharge routing. We found some way to correct for the fact that in reality you don't have steady state flows in nature. And then finally, we do pressure reconstruction in the final step. In the end, what we get is that in various types of flood events, we get really, really good behavior with 1,500 times the speed of normal flood simulation tools. So this is flash flood event, so rainfall-driven simulation. Please make sure to select the catchment, but when you do, you provide it with your rainfall data, perhaps automatically load in some land cover and infiltration information as well, or provide it yourself. And we get excellent accuracy in predicting flash flood extent. This is a small area of a part of this Caribbean island, Dominica. For fluvial simulations, the quality of the data matters a lot for the final output. So here on the top, you see the city of Valkenburg in the south of the Netherlands. Here we have the National Dutch Elevation Model, which is based on 0.5 meter resolution, 25 centimeter resolution LiDAR product. Excellent vertical accuracy, and this really helps get the accuracy of the floodplains right. And you see also that the line there, it's not visible so well, but basically it's exactly the same as what we predict with FastFlood in terms of flood extent. This is also one of the showcases on the website that you can open yourself if you're interested in looking at that. But the bottom example is quite different. This is a fluvial flood simulation in Tajikistan using SRTM. So not even the best global elevation product, I would say. And there, yeah, well, still you get a general match, but you see a lot of influence of the poor quality of the terrain model between the actual, traditional modeling on the left and the FastFlood model on the right. A recent update, part of that is already incorporated in the website, but part of that is coming in the coming weeks. So we switched the last step, the pressure reconstruction, to a cascaded profile approximation. And that really helps improve behavior in very large rivers. So in the bottom left, you see Indus Basin in Pakistan, so rivers that are a couple miles wide. And the tool did have some trouble before in spreading out the water sufficiently over the floodplains in such extreme cases. But with this upcoming update, it does that fairly easily, even at medium accuracy settings, so medium number of iterations that you give it. It does that still really well. Finally, we did a lot of comparisons between states discharge relationships where we have a bit better elevation data. So this is for the Rhine on the bottom right. You see that compared to other tools, so Manning's relationship or hydrodynamic modeling, we get also then excellent states discharge behavior for such a rapid tool especially. Demonstration time. So I'm not going to use the video. I'm going to show it to you how it really is, which is using the website. So let me do that. Let's go to FastFlood.org. This is my own local version with some of the updates that are coming soon. But if you do want to follow along, you can just go to the website. It's there. If you want to go to the documentation, there is a full additional site with documentation, list of publications so far, and the showcases that I mentioned that you can open in your browser. And that's just as simple as clicking the link, and it will open the website, automatically load the simulation settings for you, and go there as well. Takes a little bit to load the actual results. There we go. This is quite a large area, by the way, at high resolution. So this takes about 10 seconds on my laptop to run, just so you know. But anyway, let's give you a short overview of how the tool works. So in the simplest sense, what you can do is basically select an area that you want to model, and either benefit from global data sets or load your own elevation data set and run these simulations. So it's all physically based. So adaptations that you make also are automatically incorporated in the results. So here I'm loading this elevation model. This is SRTM, so that's pretty poor quality. We also offer Copernicus 30, which is a lot better. But you'll see that in the simulation results as well. So I click, and then 1-2 seconds later, I'm done. Now, SRTM, this data set has horrible issues at the coastal border. So let's select the same catchment, but download the Copernicus 30 elevation model instead, which will be a lot better. And again, if we press simulate, wait a little bit, we should see our simulation results rolling. There we go. Now, this is a very simple simulation, right? We're throwing some rainfall. We don't even know how much yet on the landscape, and we don't really have provided any detail to it. But there's a lot we can do here. So one of the things that we can start with is say, well, okay, in our rainfall settings, and now it's saying 3 hours of 60 millimeter an hour. That's a lot. It's for an extreme event on a Caribbean island pretty okay because these hurricanes are so intense. But we can automatically download design storms, select our return period. Maybe you're interested in 50-year return period, an event of 6-hour duration, and automatically load the averages into our settings. So it will go ahead. We pre-processed the ERA 5 climate reanalysis dataset for extreme events, and that's available globally. So when you, either from your own elevation model or from the global elevation datasets have selected an area, you can do this analysis on the fly and load the rainfall settings. The climate analysis takes a lot longer actually than the running the model, but you only have to do it once. There we go. So a 6-hour event has an average of 50 millimeters an hour in this case, with a return period of 50 years. Now, maybe also we want to add some detail here to land cover, to also have the frictional forces on the water captured better. We can automatically download world cover 10 meter, and it fills in automatically a land use map, different classes, and the Manning's coefficient that you would want to use there. And you can tweak these later, of course, but for now I'm going to keep them as is. And maybe as a final one for FastFlood simulation, you also want to include infiltration behavior. We can automatically download from soil grids, this global machine learning-based soil properties database, and estimate infiltration rates based on the soil properties. So again, we can go ahead, it will go ahead and automatically grab the data from their servers and fill in the infiltration rates. Let's see, turn those off so you can see what's happening with the floods again. Okay, and now maybe as a final example, we could, automatically, it will automatically correct a little bit for elevation model inaccuracies. But let's assume our elevation model is quite okay. So we can actually account also for depressions in the landscape. Let's draw some mitigation. So on the right, you see quite a selection of toolings. Those relate to things like levee systems, embankments, things like that. There we go. So you see, indeed, the elevation model did have some local depressions that are erroneous. These are not there in reality. Well, one thing we can do is automatically hydrocorrect our elevation model. Apply a hydrocorrection filter, and now when we run the model again, we won't see those depressions there, ruining our flood simulation. But if you want to include embankments as well, it's as simple as saying, let's draw them. You can later specify the height of the embankment you want, or make a reservoir. Simulate again, and it will automatically incorporate that in the simulation. And adjust the results. So there we go. It's by default, it's quite a high embankment, 10 meters, which is, well, not so feasible here. But let's say we make this a 2.5 meter one, right? You can get your scenario exploration and see what is viable, where are the issues then if you do this, where will the water go instead, etc. There's much more to the tool that I would also like to show you. So I'm thinking also a little bit what to focus on. I think I have 25 minutes left, right? In that case, let's pick another example. Maybe a bit of a larger river, right? So one of the other things that you can do is, instead of doing catchment-based simulation, you can also focus more on fluvial simulation instead, so fluvial flood scenarios. So here around Liège, let me get the Copernicus elevation model as well. Download that. And for now, maybe we say we're not so interested in a rainfall-driven local flooding. Of course, we could still do that. Maybe it's interesting to add. I'm just going to put some value for now. But that's not our main concern. Our main concern at the moment is the river. So what we can do is provide also a discharge boundary condition. So that means we have some river coming into our model domain, and we specify what amount of water per second at the peak of the event is coming into our model domain here. Now, if you're not sure what that's supposed to be because you don't have data, we have some tools to help you there. We've linked it with GLOFAS. GLOFAS is a global hydrological and hydraulic model at fairly low resolution. It runs for the entire world, and they do their flood warning system also using that. But what we can do is take their 50-year reanalysis data set and get automatically return period discharge values. So now I know that for a 50-year event, GLOFAS is saying 3,275 cubic meters a second. In this region, Globals is pretty good. It's calibrated there, so it won't be far off. For other regions in the world, you have to be careful and check. You can also get the forecast if you want to model the current values that are being predicted there. So let us put that in, and 3,275. Sometimes with the global elevation datasets, you see that there's a little bit of errors like I showed you before. So I'm just going to close off the bottom left corner with the barrier. Make sure that the water routes to the right direction. We press simulate, and yeah, again, you wait a little bit and you should see your results pop up in a bit. So again, yeah, we're combining rainfall-driven simulation together with fluvial simulation. There's some places, especially there at the start, where it's already flooding. What you do see at the end, though, the river splits in two. That's not something that the model automatically recognizes. There are other tools here that allow you to manually edit the channel routes and also output things like discharge. So if I activate that, and I also activate to automatically output the channel shape, we can also later then edit that and use these edited channel routes as input for the next simulation that we do, giving you a lot more manual control as well. And let me see the actual, oh, sorry, I forgot to enable monodirectional channels, which actually enables a lot of those channel editing tools. Now, again, there's documentation and tutorials, and if you're interested, you can always reach out. There's some YouTube tutorials on the website as well. But I think I'll keep the demonstration at this, and then we'll move on to the next aspect of the presentation. So again, these orange lines is the automatically detected channel network. You can also upload your own, but also edit it here in the tool, and then use those in the next simulation. Yeah, so there's a separate editing tool for that. Okay, then back to the slides. Now, I showed you a lot. There's of course some limitations here, right? This is we think it's really, really, really cool, but you have to keep in mind there's always limitations and drawbacks to methods. For FastFlood, it's really easy to use. In particular, for natural catchments, it's plug and play. It's nearly always really, really accurate. Fluvial floods, easy to use, but calibration becomes more important. It's yeah, that the flooding behavior is more dependent on threshold type things, right? Like levee systems, the channel capacities, etc. Which you can manually input. Maybe you can manually calibrate it, but it takes more attention to get right. For urban setting, there is often complexity due to the abundance of human interventions, lack of dominant flow routes. It works fine, I would say, but it needs some attention. You need to know what you're doing. One other thing is, for example, a lot of cities depend on stormwater drainage, sewer pipes, right, or separate stormwater pipes going underground. We don't have the option to input that yet. There's also a danger to tools like this. Ease of misuse. So we're trying to improve the design to make better choices. In one of the updates, we added also these warning icons for the hydrological assumptions, the computation time, and the final advice for will it work at this resolution? Will I get what I'm expecting? But it's also dangerous, right? If you don't know what a catchment is, yeah, people just drag a square and put in some rainfall value and then expect a flood map. But that's not what this tool is. You do need a bit of a background to set it up. You need to know a little bit of what you're doing. We try to add free and open training materials to help with that as well. Now, so this tool's been I would say, in a usable state online for now 1.5 years, something like that. We're currently getting about 3,300 unique visitors each month, typically a bit more than 200 unique visitors each day. It varies, of course. which has been really exciting also to. It's cool to make stuff that people end up using. That's really cool. I was at ETU last year, and people came up to me saying, "I've been using your website." I had no idea, which it's amazing to hear. They're using it in stakeholder discussion, a rapid explanation of scenarios. That's sort of what we envisioned. But then also, people are using it in full-scale consulting works, which also raises some alarm bells, right? Especially at the start, like, well, that's not what we intended this tool for at the start. Now we've done a lot more study showing the accuracy and the reliability of it. So it is definitely usable for hazard assessment output, but that's also a bit dangerous. At the moment, the website is not the most robust thing in the world to use in such a application, right? So we're trying to also transition maybe to more robust tooling that can work complementary to the site. It's great for stakeholder discussion and rapid explanation of scenarios, but if you want to run 1,000 scenarios in an automated way, maybe not. Right? Or maybe you want offline automated operation, you can imagine. There is, by the way, some automatic calibration in the tool. I didn't show that. Maybe we have time at the end. I also want to talk about the second tool that's very similar, inspired by the first that we're working on. So FastSlide.org, coming soon to a device running anything near you. So this is a similar type of concept. So rapid simulation tool, physically based. So you can also do mitigation and things like that, alternative scenarios. And it's using a lot of the same algorithms and techniques a little bit, but then applied to slope stability and mass movement. There's three main components in this model. Soil depth. Well, we talked about this before during the session. The reason is it's so difficult to measure and to get. So we've implemented a physically based soil depth model. Slope stability, and finally landslide or debris flow runout. Again, free, partially open source in the sense that the algorithms are, the website is not. Runs locally. That. So a bit of a methodological summary. Well, I gave that already. It uses some of the same fast sweeping methods to correct for terrain, determine flow networks. Then it uses those networks to do a lot of things later on. So the steady state soil depth method, inspired by the work behind StepDrum, but much improved now for behavior in rivers and streams. Then for slope stability, we use the iterative failure method, which is sort of an infinite slope plus. Similar assumptions, but then going a little bit further to get some lateral interactions between the grid cells in your model. For runout, we use in principle, it's a 1D Moore-Coulomb mixture runout model. And then later it does the lateral reconstruction of the lateral spread of the runout part. That reconstruction is adapted to work for slope stability. We use that same step also in the flood model, where in principle discharge is routed over this network as well. But then there's a pressure reconstruction step at the end. We do that here again, but then adapted to work for landslides, because you need to do that a little bit differently. Downstream, though, lateral spread is solved quite similarly, simply because the lateral spread doesn't occur locally; it occurs during the movement earlier on. So the results are still in that way good. Now, there is quite a philosophy difference here. Floods are easier in general, at least that might be a bit of a hot take here. But in my mind, it's easier to get good accuracy using global data sets. There's more focus on surface properties, parameters of the landscape, elevation, land cover, infiltration, which are easier to observe and parameterize. Satellites are giving a lot of information there that is really useful for flood modeling. For landslides, that's a lot harder. A lot of that is happening on the subsurface, where you don't have all that information and all those excellent global data sets. So in this tool, there's a lot more focus on calibration. I'm quite enthusiastic about the rapid calibration that we're working on, which I'll demonstrate for you as well. So a simple demonstration. This tool is indeed in the making, supposed to be done in spring. So it's really getting there, but it's not something you can go to now and try out. Let's see. There we go. So there we are on the website. I'm going to load my elevation, my own elevation model, maybe for a change. And I have a, well, let's start with the same area in Dominica. I have a LiDAR-based elevation model here. So that's, this is similarly a part of that Caribbean island. And we're offered then first with the first component of the model, soil depth. Now what we can do there is change these parameters, of course. Let's run it in first and see what we get. Takes a little bit. It's also the speed up here for the FastSlide tool is yeah, it's not going to be 1500 times, more about 500 times. This is the resulting soil depth map that you get with the current default parameters, which means that it's basically, yeah, useless. It gives you some patterns maybe that are good, right? There's more soil in the valleys, less on the steeper slopes, sure. But in terms of magnitudes, who knows? Now that's a tricky thing. Getting data to calibrate such a data set is very difficult. Maybe you use landslide scarps, and that's an option. But we went with another approach that so far has been working okay. What you said as well, soil grids also did a prediction of global soil data, soil depth. Difficulty is it's 200-meter resolution. There's no way you can use that in landslides slope stability assessment, simply because the detail is not there. You need the right spatial patterns to get the right slope stability patterns as well. What we can do, however, is say, well, download it and automatically calibrate our parameters so that on average, our predicted soil depth will be the same as the one that soil grids got in the first place. So I did that. It automatically changed the parameters here, and I can go ahead and simulate soil depth again. And what we'll see is that, yeah, we get different values that on average match the ones that soil grids has. At the moment, soil depth is way too thick for this area. It's supposed to be about 1 to 2 meters on the slopes, and now I think it's predicting more in the range of 3, 4. But with these changes, it actually does that a lot better. Yeah, so far for fast. It's slow today. I think my laptop is having a hot day today. So now we're getting 0.9, 0.8 meters. And that's just so that on average we get the same values, and then in the valleys it's 2, 3 meters. Okay, next phase, we can go ahead and switch to the stability. There's default parameters, or maybe you want to load maps. Sure, you could do that. But what if you don't have that? Well, okay, you could run the model with the default parameters, but that's not going to give you a lot of good output, right? It's default parameters. They're not there to be used like that. But again, what we can do is a rapid calibration. What we sort of did here is the following. There's a lot of global landslide susceptibility predictions using data-driven methods, machine learning, different kinds of statistical models. What we've done is taken a recent one. It's globally available, and again, what we do here is we take that susceptibility classification and inverse that to get a percentage of surface area here that should be part of the unstable classification. You can also define it yourself, but for now, let's download from the global susceptibility data. It's still, yeah, it's still in development, so it's all a bit tricky and not so finished in terms of UI. But it should be downloading that in the background, and then it should fill the value in here. Well, anyway, I know by mind what it was. And then we can go ahead and do the rapid calibration. It's going to tweak the cohesion and the internal friction angle values automatically, give them a calibration multiplier, so that the percentage of land surface that is unstable matches what I expect from my susceptibility classification. Now, again, you don't have to use this. You could use this as a traditional tool, sure, but this is sort of a way to very quickly calibrate and get to something reasonable, something that you would expect. Then in the third step, once we have our stability and our failure, so here the failures are indicated in red, we can also go ahead and do the, let me zoom in a little bit. We can also go ahead and do the runout modeling as well. And here it's sort of the same idea, physically based. It's just really fast, but still, yeah, you have to calibrate the model to make sure that it's working correctly. We're thinking about how can we also do sort of a rapid calibration effort here, how could that work potentially? But that's still in the idea phase. And here we get our runout results. Now I'm going to show you a little sneak peek about multi-hazard interactions as well. I think, yeah, you're all noticing the seismic interaction button maybe as well. That's working. You can also load global extreme PGA data for 500-year return period. But I'll skip that for now. For now, I want to load a flood map as well, because this is a multi-hazard event. We actually have a lot of flood waters during the landslides that happen here. I can load that, run my runout simulation again, and what we see is that the floodwaters dilute the debris flows and landslides, and the runout becomes significantly longer, which is what you see in reality as well. Now, there's a lot to tweak about this. This is really in development stage. We're validating a bit here and there at the moment, but yeah, because of time anyway, I have to move on. But I hope you sort of get an impression of where we're hoping to go with this. No, that's actually good to show maybe. So this is a LiDAR dam, really high accuracy. So maybe what can we do with global data sets, right? Very quickly, maybe not even using the Copernicus, but a little bit better global. So the World Dam Neo. I have a small piece in Nepal here. And again, yeah, it's just a very good way to get this this kind of rapid ideas of the processes that might be going on. Running the soil depth, running the slope stability as well, doing the rapid automatic calibration if you want, and finally doing runout. And one other multi-hazard interaction that is something that is relevant here, of course, is landslide damming behavior. So the idea is, once you do your runout simulation, you can also, from here, automatically export your elevation model, including the deposition, and then use that back in the flood model. So you have both landslide runout and deposition, but then also you can look at, is there going to be a lake forming behind this? And potentially, what are we going to see in terms of flood behavior when that lake breaches? Maybe a final thing, for both of the tools, you can export everything. Flood maps, they come out as a geotiff. So you can continue with whatever you want to do in a GIS or other software. So you're not stuck on the website. You can export anything you want. If you're missing something in the flood tool, let me know. I'll add it. I'll find a way for you to get it out of the model. So back to the presentation. So with landslide, it's a bit more tricky. There's a bit more. Oh, now I'm thinking of another thing I want to show really quickly. So let's say you have an inventory, or maybe you know a landslide source area, right? And you want to include that in the simulation. Wrong tool. Let's say you have a landslide source area, and you want to include that in the simulation. You can either estimate the volume from the area using area volume relationships. You can pick which one in the menu, or use the soil depth that you got. And then if you include it, you're also going to see that, of course, in the runout behavior. But that sort of brings me also back to an important point. There's a lot of ways to use this. Do you want to start with physically based parameters? basically from scratch, do your soil depth model, perhaps include some hydrological things, stability, and then runout. Maybe you only have source volumes and you just want to look at runout. That's an option. Or maybe you have a landslide source shapes or whatever. Maybe you made your own data-driven landslide susceptibility map. You want to feed that into the model. That's an option as well. And then you can choose, do I want to use the soil depth to get the volumes? Do I want to use the area volume relationships to get the volumes? And finally, you have the runout model. So there's sort of three ways to use it. Just a runout model, a sort of flow R type thing, or a fully physically based multi-process thing. I talked a bit about multi-hazards. So far, there's three that really come to mind that are going to be an option. There's more maybe in the future, but that's all for later. Landslide drag and dilution by floodwaters. So the lengthening of the runouts when it mixes. Landslide dam behavior. So deposition, add that to the elevation model and feed that back into the flood model. In FastFlood, you can also do dam breaching behavior. There's some data sets on dam breach peak discharges that you can use to go from lake depth to peak outflow during a breach and predict flood simulations with some uncertainty consideration as well. And finally, co-seismic landslide, I showed you already, you can load in PGA values as well. Now, to finalize a little bit, the time is also running out. Potential use, yeah, again, I mentioned stakeholder discussions. If you sit with the municipality, maybe you can sketch in real time. We're working on a bit more discussion-friendly tools as well. Colleagues from another department are working on that. Rapid assessments. Forecasting, there's a little bit of support for that in FastFlood, but we're trying to make that better. And there's some limitations, of course. The whole idea is we mainly want to provide tools for people that cannot hire fancy consultants that take many hundred thousands of euros. Nothing against that. It can be excellent, but not everybody can afford that. We want to provide tooling that's useful and might also be used everywhere and benefit from global data sets to do so. Future developments. FastSlide, it would be really cool if we can switch the slope stability also to a profile angle on the fly and do some finite element modeling also within the web-based environment, linking with these global data sets. We're doing some improved forecasting and 3D visualization. There's some MSc students working on that at the moment. We had this idea for a dam breaching, even better version for that, particularly for fast floodplains. Right, we have an embankment around an area, and the embankment fails. Things like erosion, you could imagine, might be as well adapted to work with this tooling, building on the hydrology of the FastFlood model. And processes like wind is also an MSc student is looking at. Could that even be done? And then within the risk changes, of course, there's a lot of plans to link with the risk assessment of risk changes and yeah, take input from the disaster scenario and impact pathways tools that are being developed there as well. That's it. Thank you so much.